Online students, can you hear me? So let's start at 8:15 after some. Where are the students? Last week and didn't come to class. So did you bring the theory tubes and the paper? Right. Until that, let's have a small summary of from the first theory parts that we have talked. Uh, so the unit is measurements, and so in the last unit we talk about physical quantities, right? Physical quantities. So if you take a physical quantity, it has two parts. Okay, it has two parts. So for example, if we take 5 Newton meters, it has two parts: the unit and the numerical part. So in the last class, in the last theory, we studied about this unit. Okay, we studied about this unit, and we dived deeper into these units, and we found what? What did we found? Dimensions. So we dived deep into these units, and we found dimensions. And after that, we talk about dimensions. how physical quantities are made from the root. Okay, so now from this part, I said that you have basically three parts in the first unit. In every unit, the three parts are the theory in the sense the theory related that you'll have to have before doing questions, right? You'll have to have a good theory on the subject. So that's the theory, and then you have to do questions, right? And again you have practicals. Okay, so we are still doing a revised part. So practicals in this lesson we have units, we have vectors, we have measuring instrument. Okay, so in this theory part what we did was we learned about the units. Okay, we learned about the units, right? From this practical part of the physics, we divide the physics into two parts, theory and practicals. So in practical we cover the measuring instrument. Okay, and in the next class we are going to cover vectors. Okay, it's a bit related to the second unit also. Okay, that's an intro to the second unit as well as the outro of the first unit. The first unit is going to end from vectors and start. Second unit is going to start from vectors. Okay, so today we are going to discuss about measuring instrument, right? Okay, right. So everybody receive the tutney. Okay, so online students, let me share the PDF in the group. Get ready your stuff and you'll have space in the first rows. Whenever somebody is coming from here, tell them to take a tube. Okay. Online students, I sent the document to the group, the tute. So I said you are going to have 4 tutes in the first unit. So this is the third tute, right? The third tute out of 4, the fourth tute is going to be from vectors. Okay. So for I'm using basically I'll come to those stuff. So basically there are 3 types: theory, questions, and practicals. I'm going to use 3 different colors for those different types. So this is a different colored cover. Okay. So due to some the printing shop that I'm printing the cover has suddenly stopped due to and those stuff. So that's why I move on to a little bit low quality cover page. Okay. So I hope to change it in the next tip. So these are colors. You have to get familiar to these colors. So practical tubes is going to be in this color. Okay. So online students, you can take the tube from the group. Right. So today in this lesson, we are going to do the practicals. So in practicals, we are going to have instruments, right? We are not going to do practicals without instruments. So the first unit has basically 4 instruments. 4 instruments. Okay. You take the first unit, it divided into 2 parts. Divides into 2 parts. Okay. The first one is wait. So the first one is measure units. Units. And the next one is numerical part. Numerical part. So going to the practicals, let's have a small breakdown. So unit and the numerical part. So for example, I said, let's take 5 Newton meter, the best example. So this is the numerical part and this is the unit part. So we finished learning about what? These units. Okay. So this is finished. Now we are going to move on to the numerical part. So to find this numerical part, we can do calculations, but to do calculation, you should have data, right? For data to do an experiment or some scenarios should happen there, you should take some readings. To take those readings, you should use instruments. So to move on to the numerical part, before moving on to the numerical part, we have to have a knowledge on the instruments that we are going to use. Okay. So for now, let's think about a small scenario, right? You have a man, think he's going to have physics knowledge, has a good physics knowledge, he's a physicist. And he's going to do an experiment. Before doing an experiment, you should have a what? A measuring instrument. Okay. So, and without he should have a measuring instrument as well as he's doing a practical. He should have some objects to measure, right? Not only the instrument. So he should have an object. Okay. For this, let's consider the steel here. It's much better if we can take some steel cuboid shape. So it's going to be a cuboid, a block, steel block. It's going to be a steel block. And he's going to conduct this experiment in the room temperature conditions, room temperature and pressure. So there are some external factors affecting this experiment. For now, let's consider it as the temperature. You have the temperature, right? You have the pressure, the atmospheric pressure, and you have humidity. That's humidity. Humidity is this, think it like a fog or dew. Okay, like what do we call it? Medium or something. Just think it like that atmosphere here, right? And you should have an instrument to measure and you should have an object and the external factors. So this instrument, I'm going to use a vernier caliper. Okay, out of the 4 instruments that you are going to learn in first unit, one is vernier caliper. One of it is vernier caliper. So for simplicity, I'm going to draw it like this. This is a vernier caliper. I'm going to use a vernier caliper as the instrument, an object, and this and this. So the process that I'm going to do is measurement. I'm going to measure, right? So is the 5th part here, measurement. Measurement. So how many parts do we have? Do we have factors? I mean 1, 2, 3, 4, 5. So this is the only every factor that we have, the external factor, the internal, and the things that we need, and the process we are going to do. Everything is here. Okay, these are the 5 parts. So let's think he is going to take the measurement from here. So now this is only the scenario. So from this scenario, we are going to cover up the unit and dimension and the altogether the measure practicals as well as theory knowledge to the first unit. Okay, so let's move on to a chart here. So I'm going to erase this. So you have only this. What you have, if you take the first unit, you go to the units and the numerical part. If you go to the units, it divides again to 2 parts. Okay, again to 2 parts. One is the readings that you are going to take from the instrument. Readings, and the next one is after you take a reading, you don't know if that is accurate or not, right? So if there are some errors in that practical, it's going to affect the reading. Okay, so after we are taking a reading, we should have the knowledge to know what are the errors affecting that practical. So the next part we have to have knowledge on is the errors. Okay, right? So we are going to have some errors. So first of all, we are going to look into errors before going to the reading. Okay, so you have instrument and those stuff. Basically, we are going to do look into these error types. In the A-level syllabus, you have only 2 types of errors. 2 types of error, right? One is systematic error. Systematic error. And the next one is random error. Error. Okay, systematic error and the random error. So what is a systematic error? So most of the students get confused when they are dividing what is a systematic error and a random error. So this is the simplest explanation. So let's move on to the scenario. There are 5 factors, right? I said there are 5 factors. The factors which affect the systematic errors are the man who is going to do the practical, the measuring instrument, and this environmental factor. What? The man who is going to do the experiment, the measuring instrument, and the external factor. So let me use another color. We have this. Okay, understand? This is going to be the, so don't think why I'm using a color rather than a blue color, but it's much vibrant than other colors. So you have these types, and this is going to be the what? The systematic errors. S. Okay. So if we come to errors, basically it divided into 2 parts, right? Systematic and random. So physicist has explained these 2 errors, types of errors, in 2 different ways. Okay. So the first way is by dividing them to their purposes. Okay. So what's a random error? They say the definition. Now first of all they define what a systematic error and they define the random error like this: the errors that is not included in the systematic part. Then what are the stuffs containing here without the systematic parts? The object and the process, the measurement. So this and this is going to be the random error. Okay, random error. Okay, now let's look how these errors are going to happen. Okay, so if you take a person, if he's going to do a practical, he should be a good person with a good condition. He should have a good eyesight. He should have the abilities. He should have the knowledge to think and those stuff. So when these factors differentiate, there can be some errors occurred when he's taking the measurement. For example, if you take a ruler, okay, if you take a ruler, let's take a ruler like this. It's a little bit thick ruler, a thicker ruler. Okay, a ruler. So I'm going to have a page from here to here. I'm going to measure this part. Okay. So I have the like this, the scales like this. Okay. So two of some friends, let's take two people. For one people, he's going to look this reading from here, and from here. Okay. So when he's going to take reading from this ruler, and if this ruler is transparent and if it has a thickness, so due to some physical factors, he's going to look this reading from here, this man, and this one is going to take a look from here, and he's going to take a look from here, right? So the same length is going to have how many readings? 3 readings, right? So these are the errors that's going to happen when a man is going to take a reading from a ruler, right? So these are the errors that's due to what? A person, the man who is conducting the error. So this is how a error occur by a man. So this error is known as parallax error. Okay, this is known as a parallax error. So let's go into those parts. So we come to the systematic part. Now we know the factors affecting these things. So the systematic part is going to be affected by 3 stuffs. Okay, let me write them. The first one is the instrument. Instrument. Second one is going to be the person. So it's going to be a personal error. The next one is going to be errors by the external factor. So it's going to be the external error. Okay, right? So if we take the random error, it's going to divide into 2 parts, right? Because there are total 5, and this random error is going to be depend on object and the measurement. Right. Okay. So first of all, let's look into these stuffs, errors. So move on to page number 2, executives. Move on to page number 2. So like when we are going, when we are doing a diagram, let's go move on to the theory parts and write the notes. Okay, there's a lot to fill. So first of all, we came to errors. So we are going to go to the systematic part. So what's a systematic error? It's the error that's done by the instrument, the person, and the external factors. And there's another explanation for this, what the systematic error. The next explanation is these errors, the errors done by this instrument, this man, and these external factors when we are taking measurements, now when we are doing a practical, we have to take measurement, one measurement, two measurement, and we have to move on by taking many measurements. So when we take these measurements, this error is going to get accumulated. Accumulated in the sense it's going to add up. So we can't we can't neglect the error by taking many readings and by taking the average. Okay, now just consider an example like this. We are going to measure the length of this part, this solid box, solid cuboid, this solid cuboid. Okay, let's take it as L. So one boy from here come and measure this length. It's going to, it's going to be 5 centimeters, and another boy comes and he measures it and it's going to be 6, and then another boy come and takes, it's going to be 7. Okay, now what's the best reading from here? What do you think? What will you do? Okay, one can take one of these reading, and one can take the average from these readings. So it's going to be 6. Okay, average is going to be 6. So what they are saying is, in systematic errors, due to accumulation of the error accumulate when they are going to take reading and by reading. So when you take the average also, the error is not going to get neglected, right? It's not going to get deducted. So those type of errors are systematic errors. Okay, if you take an instrument, if the instrument is calibrated with an error, let's take you go to meter ruler, let's take that. You take a meter ruler from here, here, and here, and the next reading is here. Okay, let's take this is 1, 2, 3, and 4. Okay, so one is going to likewise the previous reading 5, 6, 7. Okay, so this is going to be, let's take 6 and here is 7. So when one is taking 5, 6, and 7, and one can take one reading from these 3, and one can take the average. But if you take the average, due to this calibration error, when they are making this ruler, they have this a big gap here between 3 and 4. That's an error. So if you take the average, or if you take the just normal reading, the error is not going to get neglected, right? Due to some we would think like we took a reading and we took the average from this reading, so the error is not going to be included in the average part. But when we are taking the systematic part, the error is not going to get deduced while we are taking the average part. So we have two definitions. One is the systematic error contain are the errors done by the person, the instrument, and the external factor. And the next one is, this error cannot be deducted by taking the average, but it can be deducted by recalibration of the instrument. We can recalibrate the instrument. Recalibrating means we can take a ruler which is super accurate and recalibrate this error ruler. Understand? We can take a ruler and we can take a main ruler which is exactly accurate, and we can measure this here. So that 4 is going to come here, like that. After that, we can mark it here, and there's one, they have skipped one mark, and that's going to be 4, and these from here it's going to be 5, 6, and 7, and so on. So likewise, we can recalibrate and avoid that error, right? The next thing is, you can correct it using final adding or subtracting part. How? After taking that error, without taking the average, you can add something, or you can subtract something from the final reading. So likewise, if you take this reading, let's take, there should be one scale here. This scale is not mentioned in this ruler. So we are going to keep a ruler and find it. And after that, what we can do? We can take this and take this reading and reduce 1 from here. Okay, this is going to be 5 and this is going to be 6, right? And we can reduce again 1 from this reading and again 1 from this 7 reading. So this 7 is going to be, the final is going to be 6. This is going to be 5 and this is going to be 4. Understand? So to avoid a systematic error, you can't take the average of the readings. You should recalibrate the instrument, or you should add or subtract a fixed value from the final reading. Understand? So this is the second definition of systematic errors, right? So now let's write the definition. Okay. Systematic errors. A systematic error is a systematic error is a consistent reproducible reproducible deviation reproducible deviation caused by the instrument observer caused by the instrument observer or the environment. A systematic error is a consistent reproducible deviation by the instrument observer or the environment. So consistent in a sense that error is going to be consistent to every reading, okay, a fixed value, or reproducible deviation. So it's a reproduced one, so we can subtract it. They are saying from that word is you can subtract something or you can add it up and you can avoid that error. It's a small deviation, right? So continue to write in that part. Or environment, don't make it a full stop. After the environment, put a comma. Observer or environment, comma, which cannot be reduced by repeated measurements, which cannot be reduced by repeated measurements, but requires correction or calibration. Which cannot be reduced by repeated measurements, but requires correction or calibration. Okay. So I said that systematic error is going to get divided into three parts: the personal, the instrument, and the external factor. Okay. So the personal error is the error that we are going to when we are taking a reading due to some reasons, due to some like a disease, or if the person is not in a good condition. Let's consider he's in a little bit stressed, so, or he's a little bit dizzy, so he's going to see double, tripled scales readings or something else. Understand? So those are some errors that's by the person. And if you take instruments, there are some types of errors in instruments. So mainly let's move on to instruments. So in instruments, you have two types of errors that's going to occur. One is the calibration error, as I mentioned before. Calibration error. And the next one is zero error. Okay. So mainly calibration error in the sense the error that's going to happen due to some calibration due to the manufacturer, because the manufacturer has mistakenly put something in the scale. Okay, so let's write it. A simple thing, the simplest explanation. Under the instrument part, let's describe what an instrument error is. Errors that depends on the instrument. right? Only that. So let's move on to calibration error. A fixed error caused by a fixed error caused by a fixed error caused by incorrectly marked scales, a fixed error caused by incorrectly marked scales, comma, zero offsets, comma, zero offsets, comma, zero offsets, comma, or timing faults, or timing faults, or timing faults, not this fault, not this one, not this, faults, faults, wrong stuffs, incorrect, faults, comma, which requires instrument recalibration, which requires instrument calibration, a fixed error caused by incorrectly marked scales, comma, zero offsets, or timing faults, which requires instrument recalibration or replacement to correct, which requires instrument recalibration or replacement to correct, or replacement to correct. For another example is let's take, you all manufactured a ruler in Iceland, not Iceland, Greenland. Okay, so basically Greenland is a cool climate. I mean, the temperature is going to be in negative degrees or zero, closer to zero. Cool country, icy country. So you all manufactured a ruler like this, 2 by 2 as a scale. Okay, so let's take this is 0 and this is 1, 2, 3, 4 and 5. Okay, you produce this ruler in Iceland, sorry, Greenland, and you are bringing this ruler to here, to Sri Lanka. Okay, to Sri Lanka, and this is happening in the current situation, right? So when you're bringing this to Sri Lanka, what happens here? The temperature is going to decrease or increase? It's going to increase, right? It's going to increase. So when it's increasing, let's consider this as steel ruler, steel meter ruler, and when the temperature is increasing, this ruler is going to what? Expand. Okay, thermal expansion. Due to thermal expansion, it is going to expand. Get expand. It's going to get expand. This is going to get expand, right? So due to this, 1 centimeter in here, 1 centimeter here is going to increase by 1 out of 4 factor here. I have drawn like this. So 1 centimeter here, the original 1 centimeter here is going to be something else here. So the 1 centimeter is here. It should be smaller than the expanded 1 centimeter. So this 1 centimeter, the 1 centimeter here, sorry, not to mention it like this, much easier. So 1 centimeter in this 1 centimeter here is going to be 1 point, let's consider it as 25. This is the real length of this 1 centimeter in Sri Lanka. Understand? This is a what error? Instrumental error. Okay. So from here it's going to again accumulate. Okay. If you think this is just, it's going to increase by another 2.5 something, not like that. If it's going to the second read, it's going to be 50, 0.50, and it's going to third one, this error, this 0.25 error is going to multiply by 3, and here it's going to be like this. So for example, let's do a thing like this for your better understanding. Take this and let's keep like this. Can't change color. I'll keep like this. I'll keep like this. So this is the second reading, the third reading, the fourth reading, first reading. So if you see this gap, and if you see this gap, and if you see third and third reading, this gap, fourth reading to this, sorry, not this. Okay. So this mistaken error has increased when you are going from one reading to another reading. Okay. This is not much clearer, but I think, okay, I'll do like this. Take a blue color. So this is second reading. Reading here. Fourth reading is going. Third is. Fourth is. Okay. This difference between this red line and blue line, this red line and this blue line, this red line and this blue line, the next red line is going to be here. It's this red line and this blue line. It have increased. So this is what I said, accumulate. The errors get accumulated. So you should deduce that part from the beginning. But if you take the average, it's not going to get corrected again. Okay, this is the thing that's known as accumulated. So this is a sort of calibration error. The instrument, right? Okay. So let's look into what's a zero error. Okay, this is a little bit part that I have to explain when moving to measuring instruments. So let's move on to part. So I said that, so you have systematic errors and random errors. So if you go to readings, you have not in readings, a little bit different part, going to be another category. These are the practicals. Okay, these are the practicals that we are going to do. Okay, I said how many instruments do we have in the first unit? 4 units. Okay, 4 units. The first one is vernier caliper. There's no any order, but when I'm going to teach in this order. Vernier caliper. So you don't have a H here. Vernier caliper, it's written like this, but you read it vernier caliper. It has changed or something. So next I'm going to talk about traveling microscope. Traveling microscope. For your easiness, I have sent a small picture on this. Just check the group microscope. Check the group. You'll have the font here. I have sent picture of a traveling microscope, vernier caliper, the other 2 instruments also. So these two are a little bit similar. I'll put a small round mark here. A little bit similar. Not exactly, a little bit similar. So the next one is, the next that we are going to learn is micrometer screw gauge. Micrometer screw gauge. Micrometer screw gauge. Gauge. micrometer screw gauge, and the next one is spherometer. It's derived from the word sphere. Spherometer. Spherometer. You are going to measure something related to spheres. Okay. So in here, these two are a little bit similar. These two are a little bit similar, and these two are a little bit similar. So normally in your practical book, this is in the first place, this is in the second, this is in the third, and traveling microscope is in the last. Okay, but I have rearranged it to explain to your easiness. Okay, so if you take a vernier caliper, you'll know what? You'll know a meter ruler, right? It's easy to measure a measurement from a meter ruler, but in a vernier caliper, you have like this stuff. Again, we can divide this to some several parts. Normally, so if you are going to use instrument, you should know there are some principles that you are going to learn to measure in an instrument. Basically, there are two principles. Okay, so if you take a protractor, you'll know a protractor, a half circle, a protractor. It's going to be a curved edge, right? If you take a ruler, it's going to be a straight edge, right? So it's two principles. One is a curved one, and one is a straight edge. Likewise, if you take a if you divide instrument into two types of principles, the first one is going to be screw principle. It's a little bit much easier than this. The next one is vernier principle. Vernier principle. Okay, this is introduced by a scientist, and the vernier is a name from that scientist. Okay, vernier. So this vernier is going to get divided into again three parts. If you come to a vernier scale, if you come to an instrument which has a vernier scale, it has two rulers in it. What? Two rulers in it. What's two rulers? You have seen one ruler, you have seen another ruler. In a vernier, in an instrument which uses the vernier principle to measure the readings, it's going to use two rulers. You are going to take one ruler, and you are going to take another ruler. Okay, and let's take this ruler. What you are going to do is you are going to slide these two rulers here and there. Okay, so in a vernier, in an instrument which uses the vernier principle, it's going to have two scales, right? But not like in this case, not two rulers. One is going to be a one type of ruler, and the next one is going to be another type of ruler, right? So just for now, consider this as a meter ruler and this as a centimeter ruler, a large one and a small one. So what we are going to do, you are going to take a meter ruler and take a small ruler from your purse, and you are going to slide that small ruler by keeping it to the edge. You are going to slide this small ruler here and there. Like that sort of principle is going to use in vernier calipers. Vernier in the vernier principle. So in the vernier principle, you have basically two parts. One part you call it as the main scale, main scale, and the next one is going to be the vernier scale. The vernier scale. I'm going to introduce you all to the zero error. That's why I'm going to describe these things. So you have principles. So those principle, you have two types of principle, vernier and screw principle. Screw in the sense, just think it as a screw nut. You all know screw nut, right? Screw. Okay, just screw. Not exactly like a screw. So it's going to be a something related to a screw. So this vernier scale, vernier principle is going to use two scales. Two scales in the sense two rulers. Just think it as two rulers, and one is going to be the main scale, and the next one is going to be the vernier scale. So if we come to this part, I said that instruments, the errors in an instrument is going to divide into calibration error and zero error. Now we are going to talk about zero error. So this zero error is uh, going to get occurred only in instruments which uses the Vernier principle. What? Which uses the Vernier principle. So this zero error is included in what? In instrument which uses the Vernier principle. So simply zero error is there when you have two scales. So if you take a meter ruler, do you have a zero error in meter ruler? No, you use just only 1 meter ruler. When you are measuring something, if you are going to use a centimeter ruler, there's only one scale. Okay, don't think it as in your centimeter ruler you have two scales, here centimeters and in the next scale you have inches. I'm not talking about those type of scales. Two scale in sense you have two rulers, right? You have two rulers. Every time if they are mentioned two scales, you are going to have to think a scale as a ruler. You are going to have two rulers, two differently calibrated things, right? So the zero is going to get occurred in instrument which uses the Vernier principle. So in Vernier principle, you have two scales, the main scale and the Vernier scale. So in zero error, you have two types of zero error. One is positive zero error and the next one is negative zero error, positive and negative zero error. So now let's look into what a Vernier principle is. Okay. So now you'll have to pay your attention deeply here. So from here, only the little bit hard stuffs are going to start. Okay. So this is going to take a little bit time. So you have to give your 100% attention. So let me draw a Vernier principle calibrated. So I think I have to count this 1, 4, 5, 7. So one, right. One, two, longer. Longer. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is 1. Okay. This centimeters. So in a Vernier caliper, you are going to have another scale. So here there are going to be 10. Okay, so this is going to be the main scale, and this is going to be the vernier scale. Verniers, what? This big one is going to be the main scale, and this second one is going to be the vernier scale. So here are some 10 small calibrated lines, and here is 10 lines. So here you should know that this vernier scale has the ability to move on this main scale, but this main scale can't move. What? This main scale is a fixed one. This is fixed, the instrument. But this scale, this vernier scale, is a movable one. Movable. You can slide this vernier scale along the main scale. Right? You can slide this vernier scale along the main scale. So right. Okay. So it should be able to move this vernier scale along the movable scale. So here you should know that every time, pay attention, I said small for a minute. Every time in this main scale, the ninth smallest count is the smallest count that I can take from a centimeter scale. This is 1 millimeter. This is 1 millimeter. This is 1 millimeter, right? This is 1 millimeter. So every time is the 9th millimeter. So 9 millimeter is going to coincide with the 10th vernier small divisions. What? 9 main scale small divisions. I'll call this division as a small division. Main scale 9 small divisions is going to align with the 10th vernier small scales. Understand? Every time one part is 9, like here there is 9 small divisions. Here it's going to be plus 1. There's going to be another 1 small scale added in the vernier scale, right? So you can see that this 9 small scales is divided into 10 equal parts. These are equal calibrated parts. Due to some reason this is not like equal because I drew it. Right. So these 9 main scale parts have been divided into 10 divisions, right? 10 divisions. So one part of this small division, one part of vernier scale division is going to be equal to one part of vernier scale division is going to be equals to 9 millimeters divided into how many parts? 10 parts. So this is going to be equal to 0.9 what? Millimeters. This is going to be a little boring, but you should give your attention. If you miss this part, you are going to get messed up with vernier principle. Okay. So 0.9 millimeters. So now you all know one small division in the vernier scale. What? One small division in the vernier scale is going to be 0.9 millimeters, right? Okay. So let's go into another page. So this is the thing that we took from the previous page. One vernier scale division is going to be equals to 0.9 main scale division. main scale division. Understand? And the main scale is in what? Millimeters. Sorry, millimeters. Right? Okay. So I'm going to ask you a question. Ask you a question. What is 2 vernier scale equals to? How many number of main scale divisions? It's going to be 2 multiplied by 0.9. That's obvious, right? It's easy. So it's going to be 1.8. 1.8. So if you move to 3 vernier scales, it's going to be 2 into 3 into 0.9, and it's going to be equals to 2.7. 2.7? Yeah, 9 into 3, 2.7. Understand? So from here, you can calibrate from 1 to 1 vernier scale, and how much of the main scale is going to be equal to 1 vernier, each and every vernier scale. So likewise, I can calculate this and I can move on. So 10 vernier scale is going to be equals to 10 times 0.9, and that's going to be equals to how much? 9 main scale, and that's going to be millimeters. This is correct. This is correct. Yes. Why? We divided 9 millimeters into 10 small divisions, right? So you should know that before moving on to the zero error, now let's go. Let's see how we are going to take a measurement from a vernier scale. Okay. Only this. I'm going to erase this stuff. You all know how one part of vernier scale division is going to be 0.9 millimeters. So I'm going to erase everything. Now we'll know the larger part is going to be the main scale, and the next part is going to be the next one. So the largest part is the main scale, the next part is the next one, and what's the next one? It's going to be the vernier scale. So I'm going to erase this also. And right. Now what I'm going to do is, you should see that, let's use light blue. You should see that this is the this zeroth division of the vernier scale, and this is the 0th division of the main scale. Pay attention. 0th scale of main division and 0th scale of vernier division. So you should be able to see that the 0th scale of main division and 0th scale of vernier division is aligned. Okay. I'm going to ask another question. What's the next division in the main scale and the next division in the vernier scale that gets aligned other than the 0th one? Okay, let's look at that. So first one, is it aligned? That's not aligned. It's not aligned. There's a small gap. There's a small gap here. There's a small gap between these two. Okay. If you take the second one, there's going to be a little bit larger gap. Okay. If you go to the third, if you compare the third and the third, there's going to be another fourth, and again fifth and fifth, again sixth, again, and seventh, eighth, and if you go to the ninth and the 10th one, I said that we are going to divide 9 millimeters into 10 divisions, so that 9th division in the main scale should align with the 10th division of the vernier scale, right? That's the thing. So the ninth division in the main scale is going to align with the 10th division of the vernier scale. Okay, so this is how we are going to measure the length using a vernier scale. What we are going to do here is, we can move this vernier scale in this region, in this direction. In which direction? Only in the horizontal direction. It's fixed like this, it's wrapped around. Let's think this is a small stick, and there's a little small stick here, and what you do is, you take a PVC tube, you'll know PVC tube, and put it around this. Now you are putting sellotape with this small stick and the PVC tube, so you can move this here and there, only in this direction, here and this direction, not in this direction, right? Understand? So what you are going to do is, you are going to move this vernier scale in the main division. the main scale. So I'm going to move, I can move this. So I'm going to do a small part here, tricky part here. I know what the 0th and the 10th division in the vernier scale is going to get aligned with the main scale division at first, in the sense when the 0th division of the main scale and the 0th division of the vernier scale is going to align, the 10th scale in the vernier scale, 10th division in the vernier scale is going to get aligned in the with the 9th small division in the main scale. Understand? You should know, should have a small knowledge about that. Right. Now we know that when 0 is going to align, 10 is going to again align. Now what I'm going to do is, let's erase this. I'm going to move this in this horizontal direction. Now what I'm going to do is, this is a really hard part to me. Let's try. I'm going to move this and I'm going to get the first vernier scale division get aligned to the first of the main scale. First of all, the 0th and the 0th is aligned. Now I'm going to align the first one in the vernier scale with the first one in the main scale. Let's see it. I aligned it. Right. So now let's take again this dotted lines. So I aligned this part with the first of this part with the first of this, and now the second part, does it get aligned with the next one? Third, no. Fourth, no. Fifth, sixth, seventh, eighth, ninth, 10th, no. Now after we moved from the 0th, after we moved from the alignment of 0 with the 0 just a little bit to align with the first and the first, only one scale in the vernier scale is going to get aligned with the what? Main scale division. So remember this point. What's it? Without if we surpass the initial condition, what's the initial condition? 0th with the, let's take this as vernier scale, let's take this as main scale. 0th and 0th of the main scale is, if we surpass this initial condition, when the 0th main scale is aligned with the 0th vernier scale, apart from only this situation, in every situation only one vernier scale, this is vernier scale, vernier S, is going to align with only one, I'll write this one main scale division. What? One vernier scale is going to align with only one main scale division. Understand? But in the initial condition, two main scale is going to align with two main scale division, two vernier scale division is going to align with two main scale division. Okay, and after that again, until we align the 0th with another main scale division, only one of the vernier scale is going to align with one of the main scale. Okay, until not when we are aligning only 0th with the 0, we can align again this 0 with one of the main scale divisions. We can align this 0th with this, 0th with the second one, 0th with the third one. The thing that I explained here is, until we align the first in the sense the 0th vernier scale division with whatever the main scale division, only one vernier scale division is going to align. So when we are aligning the 0th vernier scale division with whatever the main scale, again the 10th one is going to align with some one in the main scale division. Understand? Did you understand that point? What? When you are aligning the 0th division with whatever the main scale, the 10th division in the vernier scale is also going to get aligned with one of the main scales division. Understand? Okay. But when I am aligning the first in sense this one, first vernier scale, second vernier scale, third, fourth, and fifth vernier scale until the 9th vernier scale, this 9th vernier scale, if I align one from here to here with the main scale, only one vernier scale is going to get aligned with the main scale. That one is the one that we aligned. So let's consider that I aligned the first vernier scale division with the fifth main scale division. So which division in the main scale is going to get aligned with the vernier scale? The fifth one. If I align fifth one, first one with the fifth one, the first one is only the one that's aligned with the main scale divisions. Understand? So if I align the first one, second one, third one, fourth one, fifth one until the 9th one, only one vernier scale division is going to get aligned with the one main scale division. Understand? But the next condition is 0th. When the 0th division is going to get aligned with one of a main scale division, the 10th one is going to get aligned. Okay. Now I'm going to ask. I explained you have from 0 to 10. You have divisions in the vernier scale. So I explained that if you align 0 with whatever the main scale division, you are going to get two vernier scale divisions that's going to get aligned with the main scale division. And the next one is from 1 to 9. I explained from 1 to 9, from 0 it's going to be two divisions that aligned. You go from 1 to 9, you only have this is 2. You are going to get only one vernier scale division get aligned with the main scale. Now I'm going to ask a question. How many divisions are there in this vernier scale? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and you have the 10th one also. So if you align the 10th one, okay, you have a good IQ, tell me if you are aligning the 10th division in the vernier scale with the main scale, how many divisions in the vernier scale is going to get aligned with the main scale? How many divisions? How many? 2. What did I say? I said that before, when you are aligning 0th vernier scale with the whatever the main scale, the 10th one is also going to get aligned. From that you have the answer. Understand? When you are aligning 0th from whatever the main scale, the 10th one is going to get aligned. So it's vice versa. When the 10th one is going to get aligned, the 0th one is going to get aligned. Simply that. Understand? So if you align the 10th one, you are going to get two vernier scales aligned. Right? Okay. So from here, you are crystal clear that 0th, apart from the 0th and the 10th one, you have only one main scale division and one vernier scale division that's going to get aligned with the one main scale division. Okay, right. Now let's move on how we are going to take the measurement here. Right. Okay, now let's go back to this. Sometimes when you are getting sleep here, when you understand something that's going to mind blow you, your sleepiness goes away, right? That's a small thing, small trick in physics classes as well as in maths classes. So when the theory is getting bored, you should, however, try to understand the teacher. Then you'll get sleepiness away. Right. So should I do it again? Okay. Let's try it. Happened again in which class? 2026th class. 2027th class. My goodness, I drew a beautiful diagram and everything I got lost. So you can use this time to talk with your friend. 7, 8, 9, 10. Let's see if this trick works. Okay. Okay. Right. Nothing got aligned. Wow. Right. So this is the first case. Now what I'm going to do? I'm going to bring it to align this first one with the first one. Okay. I'm aligning the first one with the first one. Right. Okay. One got aligned with the first one. Okay. So nobody get aligned when the first one is going to get aligned. So can you all see a thing here? It okay. I'll zoom it for a while. Okay, I'll zoom it for a while. Just see here. So look at the board. Look at the board. I'm going to use a small this line. I'm going to use the rule and draw a line here. Now look here. What I did, I aligned the first one with the first one. Okay, so I moved this. First of all, this line, this zeroth line was aligned with the zeroth line. So it was like this, touching it. So now I moved it in this direction. Which direction? This direction. This direction. In this direction. So I have a small gap here. I have a small gap here. Understand? So what I'm going to do is I'm going to calculate that gap. What? I'm going to calculate that gap. So first of all, it was like this. You had the main scale, you had the vernier scale, had this the first mark and the first mark of the vernier scale. The first and this is the first. Okay, first and the first. Can you see this? A little bit hard. Okay, fine, fine, fine. So that's why I use a big stroke. Okay, what I do like this is an edge, and I use like this. This is the first, and this is the first. This is the first of the main scale. This is the first of the vernier scale. Vernier and main. Okay. So what did I do now? Was only this. There's this first, and here's the first. What did I do now? Everybody, look at here. I coincided. I made this first of the vernier scale to get aligned with the first of the main scale. So this vernier scale moved from this point to from this point to this point. Understand? It moved from this point to this point. So when it moved from this point to this point, okay, this part, and it was first aligned with this part to this part. So this gap is going to be this gap is going to come here. Understand? You move this from here to here. So that gap here is now created in this space. Okay. Now I'm going to calculate this part. I'm going to do only small part like this. Only this. Look at the board. I'm going to draw. So I'm going to use the initial case here. Initial case here. So this is the first one, and this is the vernier scale. Vernier, and this is the main. So this is the smallest division in the main scale. What's the length here? What's the length here? Smallest division in the main scale. I said it's calibrated in centimeters. So the smallest is going to be how many? What, millimeters or centimeters? What? Millimeters. So it's going to be, this is going to be 1 millimeter. So according to the previous knowledge, I said we are dividing 9 of the main scale, 9 millimeters of the main scale into 10 equal divisions by the vernier scale. Understand? 10 equal division of the vernier scale. So from here I can find that 1 vernier scale is equals to how much? What did I do? 1 vernier scale, I divided 9 millimeters into 10 parts. So 1 vernier scale is going to be how much? How many millimeters? 0.9 millimeters. So this is the smallest division in the vernier scale, and this is going to be how much? People, but 0.9. 0.9, and this part is going to be how much? How many millimeters? 1 millimeter. 1 millimeter. 0.9 millimeter. So how can I calculate this gap? This gap and this gap between these two lines. 1 millimeter subtract 0.9 millimeters. That's all. So you will have to understand that now the sleepiness is going to go. I predict that the sleepiness should go. If not, you will have not understand this very well. Okay, this is 0.9 millimeters. Boys, just look at the board. Let's see how much of you all understand this. Now 1 millimeter is going to be small, tiny part. 0.9. 0.9 millimeters. So what's the answer? 0.1 millimeter. 0.1 millimeter. Now, okay, what I'm going to do is, let's assume there's a small circle, not circle, let's assume there's a square, there's a piece of square, and this length is going to be 0.1 millimeters. 0.1 millimeters. So 1 millimeter is a small part, and 0.1 millimeter is going to be much, much smaller. So I'm going to keep this small. Now I have a space here. Where? I have a space here. Here I have a space. So what I'm going to do is, I'm going to make a small here with the length 0.1 millimeters and going to keep it between these two. So I have to say another point here. The main scale is not going to move. The main scale is not going to move. So here is a small part here in this place. In which place? The main scale is not going to move. So this main scale's this part has a long wall. Wall in the sense with this. So I have zoomed this now. I'll reduce this. Okay, just the wall. What's going on here? Okay, you'll understand until that part. I'll just draw a small part. After that, when I have to explain a larger part, I'll explain you all. This thing. So here's like this. I'll draw a scratch one. I said this is the wall, and that is going to connect with the main scale. This is the main scale. Okay, this is fixed. This is the main scale. You have the main scale. Have the main scale like this, and you have the small vernier scale here. So this part is going to be the 0th. This part is going, this line, this wall is going to be with the 0th division of the main scale. So if I collide this wall with this wall, this 0 is going to align with this 0. Okay, what? I can move this. If I move this to this 0, this vernier scale 0 and the main scale 0 is going to get aligned. Understand? So is there a gap between? So there's a small part here also, but small L-shaped part with the vernier scale. With the vernier scale. So this part is going to start with the 0th of the vernier scale, and this wall is going to start with the 0th of the main scale. So when these two walls meet each other, collide, when there's no space between these two, when the space is going to be 0, the 0 is going to collide with the 0th of the vernier scale is going to align with the 0th of the main scale. Understand? Understand? Perfect. Right. What did I do now? I just do only this thing. I did this thing. I think the memory of this is full or something. So what did I do now? I moved. First, let's think it was collide. It was the 0th of the main scale and the 0th of the vernier scale is meeting each other. There's no any gap. What did I do? Now this is the 0th one. This is the first one. I aligned the first one of the main scale with the first one of the first of the main scale. This is the first of the vernier scale. The vernier, and then this is the main scale. So everyone tell me now, everyone pay attention. So this and this. Okay. So what is the gap between of these jaws? Jaws, you all know jaws? Jaw, I don't know single word. Mouth, you have two jaws, ne? Upper jaw and lower jaw. Like that, jaws. Two jaws. Like a mouth. Okay. So what's the length between this? What's it? 0.1 what? Millimeters. 0.1 millimeters. So everyone, students, just understand this. You can keep, let's think this is Ratnapura, no? Let's think a gem, a cuboid shaped gem. A cuboid shaped gem with length 0.1 millimeters. If you are going to keep this gem here, you can measure that length. You can keep this small gem to meet both of these wall, and if that is 0.1, people, now you can measure the length of this gem, and it is 0.1 millimeter. Have you ever been able to measure a length of 0.1 millimeters with a meter scale, with a meter ruler? Can you? You can't. Understand? So this is how the vernier scale work. So this is when I align the first one with the first one of the main scale. Understand, everyone? Understand? Hands up if anyone didn't understand. No. Understand? So this is scratch one. I can draw it again. So you'll understand the theory, the logics behind this vernier scale. So now think that this is the ruler, the main scale again, right? And this is the vernier scale again. Now people, I explained one example. So from that I can derive it. So let's take it. This is the second main scale division, and this is the second vernier scale division. And okay, so this is the main scale. So when you align the second and the second of the second main scale with the second vernier scale, who can tell the length between these two jaws? That's it. Just two. That's it. It's going to be, so what did I do? So again, I have to draw that diagram. I think, okay, I should practice. Let's draw it again. Don't worry. It should be much easier than. Let's draw a perfect one. But the thing is, when it gets mad. Okay, so I'm going to calibrate this. Now what I'm going to do is I'm going to calibrate this. This process is known as calibration. Okay, just remember that. I'm going to calibrate this. So 2 by 2, I'm going to keep a line here. 1, 3, 4, and 5 is going to be a little bit longer. 6, 7, 8, and 9. Ninth one and the 10th one is going to be a much longer than the 5th. Okay, so what I'm going to do, I'm going to select this whole material, duplicate it, rotate it in. Okay, so think that just to draw a vernier scale is a little bit harder than to make it. So when you become an engineer, these are the stuff that you have to do. Okay, so this is easier to me because we use softwares our faculty. So mainly we use AutoCAD. Who knows AutoCAD? What's an AutoCAD? So really beautiful. We have a subject called engineering drawing. So that's really interesting. Right, Nick? So pray to God that this won't happen again. Getting mad. So I'm going to select this, bring this here. Find this. So people soon look at the board. This is going to diminish at whatever the time. Okay. So I aligned first one with the first one. Okay, first one with the first one. So what I'm going to do is I'm going to align it with the second one. Okay, with the second one. So I have to do is I have to select this again and move it align with the second one. So I align with the second one. But every time you should every time you should remember that you are aligning the second vernier scale. Second vernier scale with whatever the main scale. Okay, but for now here we are going to align it with the second one, but sometimes we can align the second vernier scale with whatever the main scale. So first of all, when you are aligning, people understand that you are going to align from vernier scale to main scale. You are not looking at the main scale and looking at the vernier scale. First you look at the vernier scale and then the main scale. Okay, this is known as reverse engineering. So to learn this stuff, you are going reverse engineering, but to take measurements, you have to go forward engineering. So this is known as reverse engineering. So what's it? You are going to see which vernier scale align with which main scale. Okay, now I have aligned the part. Okay, whatever it is, just think this is with this here. I think there's a small Okay, so look at here. So I'm going, sorry, so I'm going to find this small length here. Okay, I'm going to find this small length here. So what happened here was, let's go to another page. So 5 pages now. The paper should have been. So I think I can delete some pages. Then I don't need. I don't need this one. Okay, okay, right. Here, what you all know is when the first one was aligned with the, sorry, zeroth one, when the zeroth vernier is aligned with the zeroth, this 945. Okay, when 0 was aligned with the 0, the first here and the first one was here. Okay, there was a small gap. Okay, there was a small gap, and when the second one was here, the second one was here. Now this gap increased. Okay, gap, I said this gap eventually increase. Understand? I showed that also. Okay, now what I'm going to do is I'm going to find this length. Okay, so first I find the length between first one and the first one, second one and the second one. So I don't want to find the third one and the third one. I can apply, I can see the pattern and I can apply to everyone. So I'm going to find the second one for you all. Okay, so what I'm going to do is I'm going to find this. So what's this length? It's going to be, this is main scale. This is how much? 1, this is 1 millimeter, and this is 1 millimeter. Totally, people, it's going to be 2 millimeters. 2 millimeters, right? 2 millimeters. Boys, this is going to be 2 millimeters. And what's the length? Now I'm going to align this and this. So I'm going to find the gap here. I know the gap here, the gap between this and this. Okay, but I don't know the gap between this, right? So this gap between this is this long one subtract this short one. So the shortest one is going to be, this one length is going to be 0.9. So there are 2 of these divisions. It's going to be 0.9 multiplied by, this is point, 0.9 multiplied by 2 millimeters. 0.9 is in millimeters, right? Okay. So the next part is 2 millimeters subtract 1.8 millimeters. You'll know 0.9 multiplied by 2 is going to be 1.8. 9 times 2 is 18. So there's one decimal place. From one decimal place, the front direction, so it's going to be 1.8. Okay. So this is going to be 0.2 millimeters. Okay. Is there anybody who can't understand 2 minus 1.8 is equal to 0.2? No, I don't think such people are here. Okay. Right. So this is going to be 0.2. Understand? So I found that one vernier scale. Boys, what are you doing here? Get the board. This is really hard to understand. So nobody explains vernier scale this much. I know it because I understand this by my own when I was doing A levels. I went to many people's classes, including sing classes, but nobody explains this much. So just pay your attention. After that, you can get accelerated when you're doing questions. Really easy. Okay. So 2 minus 1.8 is going to be 0.2. So we multiply this by 2. So when I'm going to align the second one with the second one, I'm going to make this gap here, right? I explained that. When I'm going to move this here, this exact gap is going to come here. So now I can measure a gem with a length of how much? 0.2. So likewise in here, likewise, if I align the third one with the third one, I'm going to see the length between the third one. What's the third one? 3 millimeters. Subtract 0.9 multiply by 3 millimeters, 0.9. So this is going to be 3 minus 2.7. So 30 minus 27 is going to be 3. 30 minus 27 is going to be 0.3. 3. Okay, 3 minus 2.7 is going to be 0.3 millimeters. So I can measure this much. So now you all know that when you align the vernier scale with the main scale, a gap is made in the front space in the initial between two jaws. You have two jaws. What? Two. The word is jaws. Okay, you should remember this word. JAWS. JAWS. Right. So between jaws, the length is going to this. When you align this stuff, there's going to be a small length here. Understand, between the jaws. So now you'll understand when you're aligning the first one. When you're aligning the first one, I'll erase this completely. You'll understand this theory. Now clear it out. When you understand something, clear it out. But after that, you should be able to remind it again. Okay. Now I'll go to your home. I'll provide you all the practical books, the practical book issued from the government. So from that you can see it. So I'll try if I can bring a vernier caliper here. Okay, which uses the vernier scale principle. So when the first one, the 0th one is aligning, when the 0th is going to be aligned with the 0th one, there's no any spaces between them. So what's the length we can measure? 0. We can't measure anything because there's no any space. So when we are aligning the first vernier scale with whatever the main scale, for now let's think that first one is going to align with the first main scale. So the length is going to be 0.1. So can anybody tell me, can we measure any length lesser than this 0.1? Can we? No. This is the least length that we can measure. So the least length that we can measure from an instrument has a special name. What? The least length that we can measure from an instrument is going to have a special name. For example, if you take a meter ruler, people, what's the smallest length in a meter ruler? It's going to be 1 millimeter. So that least length has a special name. Okay, so when you take a vernier caliper, this type vernier caliper, the least length is going to be 0.1 millimeters, and this length is known as the least count. Least count, which this is a length and this should have a unit. Okay, this is known as the least count. Now we will, what is least count? Tell me, what's the least count? The least length that we can take from an instrument. So come to the first page. So while we are explaining it, let's fill in the blanks. So if not, we would get rid of time. Okay, so come to the least count. First page, least count, you have space name, right? There will be a specific value. Online people, okay, if you'll have the online, you can take it from the grant, or for now you can write it on a notebook. Okay, the definition for least count. Okay, I'm going to tell the definition for least count. There will be a specific value for each instrument. There will be a specific value for each instrument. There will be a specific value for each instrument for the smallest reading. For the smallest reading, there will be a specific value for each instrument for the smallest reading that can be taken with the instrument. That can be taken with the instrument. Full stop. There will be a specific value for each instrument for the smallest reading that can be taken AEN with the instrument. Full stop. It is known as the least count of the instrument. It is known as the least count of the instrument. Is known as the least count of the instrument. So there will be a specific value for each instrument for the smallest reading that can be taken with the instrument. It is known as the least count of the instrument. Okay, now this is known as the least count, the least length that we can measure from a whatever the object. Okay, now let's look into this. So come back to the vernier principle. When you are aligning second vernier scale, let's name it as vernier scale. Yeah, aligning this. When you are aligning second vernier scale with the second main scale is going to be 0. How much? 2 millimeters. So this came from here. Okay, I'll mention it here. For example, if you take 2 millimeters, 2 millimeters minus 0.9 multiplied by 2, 0.9 millimeters, right? Millimeters multiplied by 2. Okay. If it is 3, it's going to be 0.9 millimeters multiplied by 3. Okay. So if it is nth, let's take it as third one. Okay. Third, if the third is going to align, it's going to be 0.3 millimeters. 0.3. This is going to be 0.9 times 3 is going to be 2.7. 3 minus 2.7 is going to be 0.3. Okay. So if we align the nth vernier scale with nth main scale, the length is going to be n into 0.10. Is there something as 0.8? No. Okay. What I'm going to do is, this is 3 multiplied by 0.9. Sorry, this is something. This for 1 it is 0.1. 2 0.1 times 2. 3 0.1 times 3. So n I'm going to write it as 0.1 times in millimeters. Understand? So what is this 0.1? What's it? 0.1? It's the least length. So what's the special name? It's the least count. So whatever the vernier division aligned with the main scale, that vernier division multiplied by the least count is going to give you a specific reading, and you should know that reading to measure a length in what? Using vernier principle. But the aligned division in the vernier scale multiplied by the least count. Just remember that. What? Aligned multiplied by 0.1. So there's a place to write this. Better if you can move to that place also. So we can fill one by one in page by page in this tube. Okay. So we filled the first page. So move into page number. Move into page number 11. Page number 11. So I really planned to explain everything in one place. So due to this miscorruption in this system, it's really hard. If not, I can draw the diagram with this. I drew a diagram. So we can write a short note to this specific unit. So go to the 11th page. Okay. So how did you least count? Go to the least count part. Again, you have the least count. So there you have a formula, right? You have a formula. Okay. Vernier scale is equal to 11th page, page number 11. Online students, page number 11. In the bottom part, you have an equation. So the equation to find the least count. How did you find the least count? First of all, you got that 0.1 in which place? You'll remember. How did I come to that 0.1? This got corrupted 2 times. I wrote it at first time. I said that if when you are going to align the first one with the first one, there's going to be a gap. And how did I find that gap? Subtract one main scale division by the main scale of the what? Vernier scale. Understand? So that's the formula to find the least count. That's the least count. Okay? Right. So now write the equation here. There's a subtract between two stuff. So you are going to subtract one of the main scale by the one of the vernier scale. So write in the first box here. I'm really scared to open one. Fine. You have 2 boxes minus another box. Here you have another box. So I think I have to bring the next smart board here, the old one. So you have least count. Least count it's going to be length of one part of the what scale? What scale? Main scale. Main scale. Length of one part of the main scale. Subtract. Now, can anyone translate to this part, this side? Here you should come something related to vernier scale. So here only this main part have to get differentiated. Substitute vernier to this main part. Length of one part of the vernier scale. That should be here. Length of one part of vernier scale. Vernier scale. Okay. So let's complete this page. Then it's going to be really easy. So go to the top of the page. What is a vernier scale? What's a vernier scale? I'm going to give the definition. So vernier scale is something constructed by certain dividing certain number of millimeters into some number of parts which is higher than that millimeters. So 9 we divided into 10 parts. 9 is greater than 10, right? Sorry, 10 is greater than 9. So likewise, we are going to divide some sort of millimeters into much higher pieces. So here, right in the you have a box below the vernier scale topic, right there. Scales constructed. Vernier scale, the place where you have vernier scale. Scales constructed by dividing a certain number of millimeters. Scales constructed by dividing a certain number of millimeters to a scales constructed by dividing a certain number of millimeters into a greater number of equal parts. Scales constructed by dividing a certain number of millimeters into a greater number of equal parts. Greater number of equal parts are called vernier scales. So in A levels, when you're writing anything, just stick into it what you're writing. Just think about each and every word when you're writing. So here, scales constructed. You are constructing a scale. That's what I did here. Okay. By dividing. I'm going to construct a scale by dividing. Okay. A certain number of millimeters. Okay. I'm going to take only this much of millimeters and I'm going to divide it. I didn't tell in vernier calipers you have 2-3 vernier scales. So you are going to divide this and this type of millimeters. Just only 9 millimeters in this vernier scale. So from one vernier scale to another vernier scale, now I say this is a principle. This is a principle used in an instrument. So from one instrument to another instrument, it can be changed. Instead of 9 millimeters, they can take something else. Understand? Instead of something else, they can take whatever the millimeters that they require. Okay, so 9 millimeters is here when in the example that I explained. So this is the simplest one. Okay, 9 millimeters. So I'm going to divide it number of millimeters into a greater. The word greater means you are going to divide it into greater divisions, not lesser divisions. We divided 9 into 10 parts, not 9 into 8 parts, but 9 into 10 parts. Right. A greater number of equal parts. Tell me, anyone, if you all can know the meaning of the equal. The equal here. What's equal? Which equal? Dividing into a greater number of equal parts. So we divided this 9 millimeters into 10 divisions which has a gap which is equal to each other. Okay, so in the vernier scale, you had 10 divisions, and each and every small divisions, the length between these division is going to be what? Equal. So that is what's meant here. Okay, that's the meaning of this equal. Number of equal parts are called vernier scales. Finished? So right up to that name. Okay. So let's go to the main scale. So what's the main scale? It's a fixed part in the vernier instrument. So right under the main scale part, online students, the fixed scale is a fixed scale. So write it. The fixed scale with millimeter. The fixed scale with millimeter markings called the main scale. The fixed scale with millimeter markings is called the main scale. So if you will understand word by word, you should ask one question here. Somebody should ask a question. What's the question? You should ask. No doubts. The fixed scale with millimeters. Why specifically millimeters? So instead of millimeters, think this you will use centimeters. So we are going to find something which is less than centimeters. So you have that is millimeters. You are going to measure something less than centimeters. That's why you are making a vernier principle, right? So if we instead of millimeters, if we take meters, that means we are going to measure something less than meters, something which is short, the length which has a length shorter than 1 meter. So we can measure it by a meter ruler. Why should we make a vernier? So to measure centimeter, then also you can measure it by a ruler. But to measure something lesser than 1 millimeter, so this was found. This was argued by many physicists. Like, why can't we divide a millimeter into 10 parts in a ruler? Why? Our eyesight is not that sharp. Understand? Because we have a focal point. For that we can only see this much of length. So the minimum, the least length that we can look from this eye, the eye is 1 millimeter. You can look lesser than that, but specifically specifically in prefixes, what's the base you used? What's the base of those indexes? 10. So we divide, when we are using prefixes, we divide everything by 10 or multiply something by 10. So if you are going to go from millimeters to something lesser than that, you should divide 1 millimeter into, the minimum is 10 parts. So if you divide 1 millimeter into 10 parts, you can't read it. So that's why we move on to a vernier principle. Understand? So that's why they have mentioned this as millimeter markings. So the main scale here is the main scale under the vernier principle, not just main scale. This is the definition for main scale under the vernier principle. But what have they mentioned? The fixed scale with millimeter markings is called a main scale. Understand? Sometimes you can have a main scale with inches, right? Inches, but normally, why don't we use inches? Why? Why don't we use inches in our A-level syllabus? Because it is not the what unit? SI unit. So SI unit is something that we accept globally. So when you are making an instrument, you should think about every people. So you should make it by SI unit. So it is perfect to the small full stop also. So everything in this definition has a meaning. Understand? Right? Okay. So this is what a discount is. Okay. Now let's see how we are going to measure this. So it's past 10, right? We normally start the class at 8 a.m. but normally students come to the class at 8:25. If you take the average, if last person came here at 8:30 or something, like almost 8:30. Okay, so you should come to the class at 8. Not, it's going to be really difficult. If not, it's going to be 3.5 hours. So normally every teachers in this institute is doing 3.5 hour classes, but due to me, because I need hell a lot of time to explain stuff. I explain briefly, but I need time. Okay, you need time to make something quality. Okay, so that's why I made that time to 4 hours from by requesting ma'am. Okay, so I made it up to 12. I increased the time to 8 a.m. So everyone here should be here at 8 a.m. Not compulsory. You are paying for me for this institute, so you should take a return from it, right? Return from it. So if there's no any return, you're going to waste your energy, your money and those stuff. So the special in this Grand Institute Physics class, English medium physics class, is you are going to come here for 8 hours to 1 week. Per week you are going to come here 8 hours, 2 classes, and you're going to pay 6,000, and I'm providing tubes and every stuffs. So I think that there's no any classes in this island who is going to provide these facilities in this 1,000. So you have ACs and good facilities in the institute as well. So every time this should be a discipline in you all, understand? So you should be able to use the utmost that you all can for what your mother is providing. Okay, mother or father is providing. Okay, right. So if I have to give you all a break, I should give it as 10:30. But since I'm going as a timetable, I'm going to give it at 10. I started this at 8. You all came at 8:30, but I started this at 8:15, right? Because I gave time to come some people to get arranged. So take the interval. Now it's 12. Sorry, it's 10:10. Come at 10:25. Come at 10:30. 50 minutes you all won't come. So please be present here. So this is a little bit a seminar type. I won't complete this in 2 days. Okay, right. Online people, what's your name? And Russia, you have logged as and Russia. Your name is Anora. Eh, Anora, right? So you'll have to write everything in capital letters. You have the NIC number, gender, read those stuffs. So for this, I haven't given you instructions, but I have given a sample of somebody else information. I mean, an unknown person, a random person, okay, AI generated one. So no any instructions, just look at that example and think how you have to fill it and think, fill it, okay, right? So I'm going to pass this from here. Take one paper. Here you can tear it off from here. Okay, you can tear it off, and pass this to the next one. Okay. Oh, all right. So first of all, I can send it from your side. Take it. Have two dotted lines. Get it from this, not this, from here. Take one paper. Start here. Likewise, tear it. It's small. The font size is very small. Okay. Try to write your letters inside that. So before tearing it, I have mentioned that you agree to terms and conditions by tearing this. Okay, just read it. Okay, fine. Terms and condition means I'm asking your permission to collect your details, and this is privacy. I'm the only ones who is accessing your these informations. This is not public. Likewise, I'm going to put this into a database. So I'm going to give you all student IDs. So likewise, I'm going to collect that attendance and those stuff. Okay. For that only, I'm taking these informations. So what you have to do is, while you are when I'm teaching, you have to look at the board as well as you have to fill this. Okay. I won't give I will give you 5 minutes to extra 5 minutes to fill this stuff, but mainly try to fill it when you're learning, okay, when you're studying. Okay, so the next thing is, okay, so when is your all the results are coming? What to come? Which month? Don't know. This month? This week? My goodness. Hey, congratulations. But after your results are released, don't change your stream. Okay, most of the students just that's like after 1 month they're changing the stream. You can do it. You thought, you planned, you have to step into that. Okay. Now we are in measuring instruments, right? Measuring instruments. So I think it's much better if I give you all time to fill it. Not now, not now. I mean, keep it aside. If you'll have fill it halfway, keep it aside. Okay, keep it aside. Just at least mention your name. So whenever it's mixed up with your friends, you can recognize it and take it. Okay. And check if you'll have two applications. Sometimes mistakenly you would tier two. It's okay, but right, there's a small instruction below it. That's not instruction. That's these are for what stuffs I'm using these informations. Okay, it is mentioned, and I have mentioned that. So I can't take your signs. Okay, I can't take if everyone's each and everyone's signs. So I have mentioned that when you are tearing, so everyone teared it off. When you are tearing, you are agreeing to this. You're giving the information like small stuff. So I should have permission to collect your national IDs. I need that to take some information from it. Okay, right. So if I take the national ID, I don't want to ask your birthdays and stuff. I know those stuff. That's why I just didn't mention that. Okay. So right. Now let's go to the lesson. So people who have huge letters like big, try to minimize your letters. Okay. Most of them don't have like stuff like twice letters. Okay, right. So we were learning about vernier calipers. So However, when you have an interval, I made a vernier caliper by my own. Okay. Now look at this. Is it hard to tear? Hard. No, ne? And tear, ne? So please don't get corrupted. So what I did was, I said that, let's go to this page. I said that I'll use this to write the notes to explain stuffs. So I said that the gap between these two jaws, the gap between these two jaws is going to be equal to the length of the object, length of that stuff. Okay. So the gap is the length. We are finding the gap. I mean, starting from this jaw, let's name this as the what jaw? These two are jaws. This is main scales jaw. This is vernier scales jaw. This is the fixed jaw. This is the moving jaw. Okay. Starting from here until this, until the starting point of the sliding jaw, the length between these two is going to be equal to the gap. Okay, this is the gap. So finished. Okay. Online people, you can hear me now? So what about online students? Can I get it from the institute? Yeah, you can get it from the institute. I'll keep it here. So I think you come to the evening classes to the grand. So just tell Manjula that you need this application, and I'll give her, provide her. Finished. I mean, you teared off. Have messed it up. All right, fine. So here's the thing. Shh. I'm going to explain you a different stuff. Okay. What did I say? The reading that we are going to take here, the measurement here is the gap between these two jaws. If this gap is 0, the reading should be what? The reading should be 0. Okay. This boy, can you come a little bit to the left? Little bit. Fine. That's it. I can see you. Fine. So the reading here, the gap between these two jaws is going to be the reading that we are going to take. So if the gap between these two is going to be, if this gap is going to be 0, I mean, this wall is touching this wall, right? This wall is touching this wall, no any spaces. So the reading should be what? 0. I mean, the 0 of this vernier scale, 0 of this vernier scale, this is the 0 of this vernier scale, and the 0 of this, 0 of the main scale, and the 0 of this vernier scale should align. Okay, then only we can take the reading. So when 0 is aligned with the 0, what? I'm going to write it in a different color. Let's use green. When vernier scale 0 is aligned with the main scales 0, the reading is going to be 0. Reading is going to be 0. Fine. When 0 is aligned with the 0, it's going to be 0. So when the vernier scales 1 is aligned with the main scales 1, I mean the smallest scale in the main scale and the smallest scale in the vernier scale, when it's going aligned, then what's the reading? What's the gap? 0.1, and that's the least count. 0.1. Fine. 0.1. So likewise, when second means let's use this 0.1. So think about this. What? think about this. Let's think about this reading. Think about this reading. So the reading is 0.1. So this 0.1, this length, this is the reading. So this length should be equal to what? Equal to the distance between these two jaws. Distance between these two jaws. Okay? So this 0.1 should be distance between these two jaws. The next logic that I'm going to come is the wall is aligned with the 0 of the main scale. The wall here is calibrated as 0. The wall calibrated here is as 0. And the wall calibrated here in the vernier scale is the 0 of the vernier scale. Okay. So I came from here. First what I said the gap is going to be the reading. Now I came to the reading. I calculated the reading. I aligned first vernier scale with the main vernier scale, and the reading is 0.1. I calculated it. So this should be the reading, the gap between these two jaws, right? These two jaws. So these two jaws, the starting and the end, the starting point of this, that's going to be the 0, calibrated as 0 of the main scale and calibrated as the 0 of the vernier scale. So people tell me, then can we tell this like this? So 0.1 is the distance between the 0 of the main scale and the 0 of the vernier scale. The distance between 0, I'll put 0 like this. This is 0. Okay, for now. 0 of the main scale and the 0 of the vernier scale. Understand? Okay, who didn't understand this? What? This distance, the gap, we can tell it the gap between the jaws or the reading. Everything should be equal to the 0 of the main, the distance between the 0 of the main scale and the 0 of the vernier scale. So 0 of the vernier scale, main scale is the jaw of the main scale. 0 of the vernier scale is the jaw of the vernier scale. Understand? This I can equal this to what? Main scale jaw. Main scale jaw. Is it okay? Why? Main scale's jaw starts from the wall is calibrated as 0. Fine. So the 0 of the vernier scale is calibrated as the jaw of the vernier scale. Vernier scale's jaw. Starting point. Here I'm considering starting point. Starting point in the sense the jaw starts from here for the main scale and the jaw starts from here for the vernier scale. So this main scale's jaw and the vernier scale's jaw is calibrated as the what? Calibrated as the 0 of the vernier scale and 0 of the main scale. Okay, this is for your easiness. This vernier caliper I have drawn is for your easiness, but I'll tell you how an actual vernier principle is applied. So if the distance between the zeros of two readings, 0 of two scales, now I have come to a conclusion. The distance between the 0 of the main scale and the 0 of the vernier scale is going to be the reading. That's the reading. That's the conclusion. Understand? The distance between the 0 of the main scale and 0 of the main scale and the 0 of the vernier scale. The distance is going to be the length, the reading. So let's come to this point. So what I'm going to do is, if the jaws touch, the 0 of the vernier should align to the 0 of the main scale. I'm telling this again and again is because of this stuff. So the conclusion is, when the jaws touch, when the jaws touch, 0 of main scale should be aligned. I'll write aligned as middle, aligned with the 0 of vernier scale. When the jaws touch each other, okay, when the jaws touch each other, 0 of the main scale should be aligned with the 0 of the vernier scale. Okay, understand? So, what if this happened? Okay, this is a steel. Normally, vernier principle is used in a vernier caliper, and vernier caliper is made by steel. Okay, stainless steel. So, what if something happened and these jaws get worn out? Worn out means ගැවිලා යනවා. ගැවිලා යනවා නේ. ගෙවිලා යනවා කියලා කියනවනේ. I mean, it's worn out. Steel, it can get worn out. You think you put a metal diamond between these two jaws, it can get damaged. So if this jaws get damaged, think like this. If this jaws get damaged, I'll move on to this part. This is the jaw and this is the next jaw. Okay, right? Think this got damaged and this happened. What? This got damaged. This got damaged and this part worn out. Okay, think theoretically, yeah, not practically, just think theoretically. So this part worn out. Okay, now the jaw is starting from this dotted line. Now the jaw is starting from this dotted line. So now this part is not there. Now I'm going to, I can move this vernier scale. I'm moving this and I'm touching this. Where? This dotted line and this line. So these two jaws touched, but still the reading is 0. Why? When the jaws touched out, the reading should be 0. Should be 0. But here, what happened? The jaws touched, but the reading is not 0. Not 0. But we considered, when we made the instrument, we said a statement, the distance between the jaws is the reading. Distance between the jaw is the length of the object. So now this is worn out. So now this is touched, but the distance between this is 0. But there's a reading. Understand, people. The jaws touched, but there's a reading. It can't be happened. Why? If there's no distance between the jaws, it should be 0. But this worn out and this touched. So there is an error. Understand? Okay, I will explain this briefly by using a vernier calipers diagram. Okay, vernier calipers diagram. So when this is worn out, this jaws touched. Now the new jaw is here. But the new jaw is here. Okay, new jaw is here. So I'm going to erase this part. I'm going to erase this part. So I take a small gem. I take a small gem. Okay, I take a small gem. Let's take a small shape. Beautiful one. Let's take this bowl. Okay. Now previously that ball was here. No silly stuffs. This was here between these two. Okay. Then there was a reading. There was a reading. So I can't erase this. Okay. So previously the line was here, right? Previously the line was here. Stop talking. It was here. And now let's assume that the diameter, this is, we are measuring the diameter. The diameter is 5. Let's take it as 5 for now. 5. Okay. But this part worn out. Now the 5 of something is, let's take it as 0.5. 0.5. Pay attention. 0.5. Okay. Then the 5 of the vernier scale is aligned with the 5 of the main scale. You can remember that. 5 is aligned with the 5 of this. So now this part wound out. Wound out. So I can slide this furthermore. In which direction? In this direction. So now what happens? Now this 5 is not going to get aligned again. Now this part is going to go this much further. So something greater than that is going to get aligned. Lesser than that. Sorry, lesser than that. What happened? First of all, this is the slide. This is the vernier scale. This is the vernier scale. First of all, in the initial scenario, we move this in this direction. We move this in that direction to align 1 and 1, 2 and 2. So when we move in this direction, the reading increased. The reading increased. Understand, people? Understand? When we move the slide sliding part in this direction, the reading increased. Reading increased. I'll put it as R. Reading increased. Okay. Now this is worn out and this is sliding to this direction. So if it is slide to this direction, if the same thing is going to slide into this direction, it should be the opposite of this. That means it should reduce, right? Reduce. So this is going to reduce. The reading is going to get reduced. Reading is going to get reduced. People understand? So now the new reading after this is worn out. The actual reading was 0.5. Now this is worn out. Now I'm taking the radius again. This is a new vernier caliper damaged, and I'm going to take the radius again. Now the new reading, I'll take it as this part. For now, I take it as this. This is the new reading. Sorry, I'll take a king's crown. Okay, this is the new reading. This is the new reading. Okay, now this new reading is here. Okay, I take to it from the new reading. So this is a numerical value, right? I just used object, but it's a numerical value. So tell me, people, if I put a box here, which one is greater, the crown or 0.5? One is greater. Think, logics, think. I slide it in this direction, this got worn out. I slide it in this direction, now the reading getting reduced one by one. So now the new reading is this crown. So this reading should be greater or lesser? Lesser than the initial reading. Understand? Initial reading. I'm writing the crocodile mouth in vertical direction. Okay, this is a crocodile mouth. Wait, you're going to mess it up. So I'll write it again. Okay, no silly stuff. Actual mathematics. Let's assume the new reading is n. New reading is n. Okay, so this is less than 0.5. Okay, so I'm going to write it in a verbal form. Now, no, I'll explain this and I'll write it in literal form. Understand? Now what happened? The new reading is lesser than 0.5. So let's assume that this particular n is equal to 0.3. Okay, 0.3. 0.3. Understand? But is it the diameter of this circle, people? Is it the diameter? No. The actual diameter was 0.5. Okay, when I was buying this ball, he said this sphere's diameter is 0.5. So when I measured it initially from a new vernier caliper, the reading was 0.5. But after some time, it wound out. Now the reading is 0.3. Now tell me, is there an error or not? No or yes? Is there an error? Yes. Understand? There's an error. So this should be corrected as 0.5. So we should add something to this 0.3. Understand? We should add something to this 0.3. So now when I am coinciding this, the imaginary 0 mark, that's here, this here. So this worn out, I am joining these two, the worn out vernier caliper. So with that, the imaginary 0 is going this direction. Understand? The imaginary 0, that was worn out. That was worn out, right? Understand? The imaginary 0, the 0 was here. I said the 0 is here in this wall. Now it just got worn out. So now the 0 is not there. Understand? Understand? So now when these two lines coincide, I mean, let's take it as coincide. This wall and this wall came nearer and this coincided. Okay, this coincided. No any gap. So now the imaginary zero is here neither. Now the imaginary zero is here neither. Understand? It moved to this direction. Understand? So the zero. So I'll take apart from here. I'll take apart from here yellow color. Take it this a zoomed figure. What happens here is it's like this. There's this big L here. There's the small L here. The zero is here, and the imaginary zero is here. Understand? So the zero traveled in negative direction. So this sort of error is known as zero errors. So let me ask a question. So the errors caused by the zero. This is caused due to the zeros moving that direction. So this is known as the zero error, and the zero errors occurred like this, and because it moved in the which direction? The negative direction. We take this as the reference. It moved in the negative direction relative to the main scale. Relative to the main scale, it moved in the negative direction. So I said that before. So I lost those diagrams. So I said that zero errors is categorized in two parts. One is negative zero error, and I said the next one is positive zero error. I mentioned it. So now we learned about negative zero error. Negative zero error. Negative zero error. Okay. So to correct this, move into this page. Okay. Now the reading is 0.3. To correct this to 0.5, I should add. I should use a positive number. Understand? A positive number. So this is a positive correction. This is a positive correction. So this negative zero error, this is the just name, calling name of this error. Just like, what's your name? You said Vihanga. His name is Vihanga, but he has a surname, right? So you can call with both of that name. Likewise, this is just the error's name has an elongated form, and that part is negative zero error, positive correction. So by knowing his surname, you can think from which like you can know some stuff about his family name. You can know much more about his family by knowing his name. Like it can be his father's name or grandfather's name. Like that name, you get the surname. Likewise, from this you can take an additional information about this zero error. What's it? Negative zero error. We added a correction, and that is a positive correction. Understand? Understand? This is a negative zero error because the zero moved in the negative direction. So we have to add something to come to the correct solution. So negative zero error, positive correction. Remember that. Negative zero error, positive correction. So I'm going to write it here. The next name is going to be positive zero error. Positive zero error. Then what would be the surname? For now, I'm calling it a surname. What's the surname here? Negative correction, right? So positive zero, it's going to be negative correction. Understand? Right? Okay. So these are the two types of zero errors. So I explained how a negative zero error can occur, right? So now let's talk about positive zero errors. Okay, positive zero errors. And we'll see if this logic is correct. But if it's a positive zero, do you want to subtract something? Okay, let's see it. So here, people, I'll keep it like this, and can I duplicate it? No, I don't want. So I'll draw a small diagram and ask a question like this. So tell me, yes, any people can answer this question. Just take a small rod. Okay, metal rod. Take your hands from it. Don't sleep. This is really interesting. Now it's going to be interesting. So this is a metal rod. Okay, metal rod. This is a new metal rod. I bought it today. And gradually, this when it metal reacts with oxygen, what did it occur? What will happen when it reacts with oxygen? It corrodes. The metal gets rust. If it's iron, it's going to be get rusted. Okay. So with time, let's think this is going to corrode. Okay, corrode. So let's assume that this part is going to get corroded away. This part is going to corrode away. So sometimes this will just corrode, and if somebody touch this part, this is going to fall down. But until that, before you are touching this part, is when this is going to corrode, what happens? This exact volume is going to increase. That's known as corrosion. Corrosion in the sense is going to react with another element, and the final volume or the final area, let's assume let's take the volume is going to increase. It's going to increase. Just take something, measure its volume, however, okay, and after it corrodes away, measure its volume, the volume has increased. For example, have you seen this in YouTube shorts? I think you will have seen this. But they take a gold something, and they react it with mercury. They put mercury into the gold. So just ask from your parents, is it okay to keep a thermometer, mercury thermometer with gold substance, gold earring or something? They said not to keep them. Why? Gold corrodes, reacts with mercury, and it corrodes. It gets reacted, and so we call it as a corrosion. So after it's corrode, if you take a small tube like this, the thickness, take it as a small tube. So if you put some drops of mercury, this get reacted, and this cube just elongates. It becomes long like this. It's like when you put mercury into it, it gets elongated. Everything comes out, like sort of thing. So the volume is going to get increased. So likewise, so why I took this example is when the corrosion happens, the volume gets increased. The volume gets increased. So I'm going to use this exact example and teach you all this. So you have the main scale, right? You have the vernier scale, a new one. Okay, this part is vernier scales, sorry, main scales. This part is vernier scales. You can see it. This is the main scale. This is the vernier scale. Okay, so after some time, this didn't get worn out. This is a steel or something happened. This corroded away. Only this part or these two jaws, whatever the parts. Okay. So what happened is this part. Every time we are touching this part, so after the coating of this get removed, and the steel part came out, and let's assume that it corrodes. It get corroded. So what happened is this volume in this of this jaw is going to get increased by this much of amount. Understand? Simple thing. Understand? So first of all, what happened? So for now, for simplicity of understanding, I'll erase this part. Which part I'm going to erase? This part. I'll take only the which jaw, the sliding jaw corroded away. The sliding jaw corroded away. Just assume like a simple explanation. So what happened is, first of all, the zero was here. Sorry, the zero was here, and now the zero is here. When I touch both of these jaws, what happened? There's going to be we can't see this corroded part. Sometimes the corrosion can occur in the interior part of this when it can get elongated. Okay, the volume can get increased. So however, the zero is going to get elongated. So this is the nib jaw, and this is the main scale. This is the main scale. This is the vernier scale. So previously the zero was here. The zero was here. Vernier scales 0. Vernier scales 0. The vernier scale 0 was here. But now it's getting touched. The 0 of the main scale was here. Okay. Now there's a small gap. But this jaw is touching, right? We touched these jaws. This jaw is touching. So the jaw is touched, but there's a reading here. Why? If the 0 is not aligned with the 0 of the main scale, then somebody from the vernier scale is going to get aligned. Understand? Okay. If somebody is aligned with a different member of the main scale, there should be a reading. Okay. But that reading is not 0. Why? Because this 0 is not aligned with this 0. What are the logics? This 0 is now not aligned because the jaw corroded away, and this is the new part. Now we joined it, the jaws are touching, but what's the logic we used? If the jaws are touching, the reading should be 0. But here jaws are touched, but the reading is not 0. Why? Because these zeros are not aligned. That means somebody is aligned, then the reading is we read it respective to the aligned people of the vernier scale. Understand? Understand? So there's an error. So jaws met, but not 0. Understand? So initially, let's take the same example, a ball, and this is between these two stuffs, before this corroded away. Okay, let's take this as, let's take it, the diameter is going to be 0.5. The diameter is going to be 0.5. That means vernier scale's fifth vernier scale is going to align with the fifth of the main scale. Fifth is going to align with the fifth of the vernier scale. Understand? Therefore, the reading is 0.5. Okay? Understand? Right. So what I am doing here is, now I am going to keep the same ball. I am going to keep the same. Let me erase this. No, I'll take another ball. Take another ball, and now I'm going to keep this between this. The new, it corroded away, right? Understand? This is the same exact ball. You'll misunderstand. I'll do like this. So I took this ball away. Now I'm moving this here and there, and now taking the same ball again, and now it is corroded away. Now after it corroded, I have to keep this between this. First of all, I kept it between red lines. Now I'm keeping it between red and yellow lines. Understand? Understand? So I'll take like this. Okay, like this. So what I'm going to do is, I'm keeping this, and now to use this yellow colored line, to meet this yellow color line to this edge, I have to slide this vernier scale to this direction, right? Meet the yellow line to this edge. Understand? To make, what I'm going to do? I'm going to make this circle, this circle sphere. I'm going to touch this yellow line in here, from here. Keep it between these two jaws. After it corroded. Understand? So to meet this yellow line to this sphere, I have to move this in this direction. Which direction? In this direction. So again, I'm going to go back to the theory. What? When you're moving the vernier scale in this direction, so to align one with the one of the main scale, we moved it in this direction, right? So the reading increased 0.1. So after then we aligned to second vernier scale, so it became 0.2. So eventually it increased. So when we are sliding this vernier scale in this direction, the reading is going to get increased. The reading is going to get increased. Okay. Now first of all, it was 0.5. So after this vernier scale corroded away, now the reading, let's assume it is n. So if anybody can tell me, is greater, which is greater, 0.5 or n? 0.5 or n. So I slided it here to match with this yellow line. Understand? So the reading increased. So the reading increased. So the new reading is greater now. Now the new reading is greater, because when I'm sliding this direction, the reading is going to get increased. So the reading increased. So the new reading is n. The initial reading was 0.5. Now this n is greater than this. Okay. let's assume that this nib reading is greater. Let's take it as 0.7. 0.7. The nib reading is 0.7. So this nib reading to be corrected as 0.5, but the actual reading is not 0.7. The diameter is 0.5. To make it as 0.5, I have to reduce something. I have to subtract. So I have to correct it by a negative number. Negative correction. Negative correction. Understand? Negative correction. Okay. So this is what I explained. So this is the 0 moved. So when I'm so let me take like this. So here, if I join before it is corroding, I can align 0 with the 0 before it's corroded. Okay. But now I'm aligning this part, this corroded part with the 0. So the 0 here has moved to this direction. The 0 is here. Now the vernier scale 0 is in this direction. So relative to this 0, this direction is the what direction? Positive or negative direction? Positive direction. So the 0 of the vernier scale have moved the positive direction. So this is known as what 0 error? Positive 0 error. Okay. This is known as the positive 0 error. So this is known as the positive 0 error, and it is corrected by a negative correction. Understand? You have to see the negative correction. So however, we have to find this number. Which number? The value that we have to add or we have to subtract. In this case, it is the difference is 0. How much? 0.2. 0.2. Okay, 0.2. So we have to add 0.2 to correct this. In this case, what's this? This is also again 0.2. We have to subtract. Minus 0.2. Here it is plus 0.2. Plus 0.2. Okay, right? Plus 0.2. Now what I'm going to do is, now I'm going to find this reading. How to find this reading? It's simple. When, what's this example? This is the worn out part. So this worn out, from here to here, when this met, it is 0. Now this part and this part is going to meet. What? Let's take a different color from here. That's it. So first of all, we measured this distance when this initial, before this is getting worn out, when we when we collide these two walls, it's going to be 0. Okay. After this worn out, and now the gap is going to be from here to here. Then it has a reading. So that reading should people the distance from here to here. Right? We are measuring this distance now. Why? This is touching. So before, when it touched here, 0 of the main scale aligned with the 0 of the vernier scale. 0 of the main scale aligned with the 0 of the vernier scale. But when I'm moving much further, 0 is not going to align with the vernier scale 0. Then there should be something aligned. There should be something aligned. So from that we can take a reading. From that we can take a reading. So that reading is the reading of this error. Reading of this error. So if we go to this here, now what is this? This is an extra part. Extra part has been added. So between these two lines, the theory was the distance between the 0 division is the reading. So the distance between these two is going to be the reading here. If I'm going to take the reading by the vernier scale, looking at which vernier scale get aligned with the main scale, then that reading is related to this gap. Why? 0, when the length between the two 0 divisions is going to be the reading. Understand? So that reading will show us 0.2. So that 0 point should be negative 0.2. This negative we should come from, this is a positive 0 error. So this is a negative correction. The value, only the magnitude, we are going to find it by the reading. Likewise, this is positive 0 error, negative correction, and the value is 0.2. And here, this is Negative 0 error. This is a negative 0 error because the 0 traveled in the negative direction. Negative direction. This is negative 0 error. So we use positive direction. This numerical part we found by the reading. Understand? So when these two touched, when the jaws touched, we say that the distance between vernier scales and the distance between the zeroth division of the main scale is going to be the reading. So this reading is shown here, somewhere here in the instrument. Okay, so that reading is 0.2. Understand? But this symbol, this positive or negative stuff, we have to look if it is a positive 0 error or a negative 0 error. Understand? Okay. Likewise, this is the explanation for 0 errors. Okay. Now let's go to 0 errors. So 0 error, you have a small definition. So examples for 0 errors I will give by using papers. Okay. 0 error. Go to page number 2. Page number 2. In instruments that use two scales, 0 marks of the two scales are not aligned. Percent 0 error simply. In instruments that use two scales, 0 marks of two scales are not aligned. Okay. 0 marks of the two scales are not aligned. Are not aligned. Okay, finished. Right. So that is the explanation for 0 error, and we'll learn about 0 error furthermore when we are doing the exact vernier caliper principle practicals. So after that, we learned about vernier principle. Okay. So let's go to page number 15 and fill in the blanks. So in the lower part, this is how to take a measurement from, did I mention it? Okay. This is how to take a reading from what? Reading from a vernier caliper. Okay. So reading is equal to, so in the lower bottom part, you have a formula, right? You have a formula. So in that formula, you have a box here that's equal to, right. I'll take any. So there's a box that is the reading that's equal to this plus something multiplied by something. Okay. Now let's look how to take a reading. So here, that's it. Here, you have to write the thing. Right. No, you can't write that because reading have to add something. Okay, we just need another theory. Okay, let's move into that by talking about all the every stuff here. No, don't go to that page. We can't write it because there's a small additional part to solve. Okay, so first of all, let's finish the errors. So we said that there are systematic errors. There are systematic errors. Wait, people. There are systematic errors and there are random errors. So let's finish this stuff. Systematic error. Systematic errors. You have how many? You have 3 categories. One is instruments error. Instruments error. Instruments. The second one is personal error. And the next one is environmental external factors. By external factors. External factors. External factors. So we looked into the instrumental errors. It's calibration error, calibration, and zero error. So this is finished. Now let's look into personal errors. What are the personal errors? So in personal errors, you have two stuffs. You have only one. They have mentioned only one. Parallax. Yeah. In personal error, mention it as you have a small part to read right there. Under personal error, we finished systematic errors. Now we have to move. Yeah. So under personal error, write it. These are the errors that occurred by a man who's taking a measurement. Personal error is personal error is variation in result. Personal error is variation in result. Variation in results due to individual differences like reaction time. Individual differences like reaction time. Due to individual differences like reaction time. Individual differences like reaction time. For one of the example, for there are many personal errors. So I have mentioned only one. It's the parallax error. The parallax error. So what's a parallax error? Parallax error is occurred due to the thing that I mentioned before. That is, when you are going to take a measurement, when you are going to change your point of view, the angle, the error, the measurement is going to be different if you are going to read from a ruler. Okay, that's known as a parallax error. So let's write there. I have given you a small diagram to understand it better. So under parallax error right there, parallax error is a personal error. Parallax error is a personal error. Arising when the observer's eye is not positioned perpendicular to the scale. Is not positioned perpendicular to the scale. Perpendicular to the scale. Causing perpendicular to the scale, comma, causing apparent displacement of the pointer. Causing apparent displacement of the pointer. Causing apparent displacement of the pointer. And causing apparent displacement of the pointer and incorrect readings. Okay, right. And incorrect readings. So in personal error, we looked into parallax error. What a parallax error is. Just one example. So for external errors, there are a lot of external errors. We are not going to deep dive into external errors by the environment. I'm going to give the definition and I'm going to tell you all about other stuffs. Okay. So for the external error part in the next page number 3, error created by external factors. Error created by external factors. Right, I would read it. Systematic deviation caused by, start right. Systematic deviation caused by environmental conditions. Systematic deviation caused by environmental conditions such as temperature, pressure, humidity, systematic deviation caused by environmental conditions such as temperature, pressure, humidity, affecting instruments, affecting instrument performance, affecting instrument performance and measurement accuracy. Temperature, pressure or humidity affecting instrument performance and measurement accuracy. For an example, I can tell that the example that I took from you manufactured a ruler from Greenland, brought it to Sri Lanka. So there's an expansion due to that temperature difference. There's an error occurred. So it falls under external errors. So here mainly you don't have to remember. There are many examples. So this personal error is not going to divide into basic factors, normal parts. But instrumental errors, you have only calibration and zero error. And here again, zero error is divided into two parts: positive zero error and negative zero error. Positive zero error and negative zero error. Okay. So in systematic errors, it's hard to calculate the errors from the external factors. It's hard to calculate because a lot of stuff affects these experiments. So in advanced level, we are not going to see how the external factors affect and how to calculate those errors, and we are not going to use in engineering when we are doing after advanced levels. There are calculations to find the personal errors as well as the external factors. But here we are not going to look into personal errors as well. The errors, we are not going to calculate the personal errors. There are some calculations. It's basically max based calculations. We are not going to find the personal error, calculate the personal errors. So here the calculation part is only involved to systematic error. It's only involved in zero error. So it's going to be included only in zero error. So in advanced level, you are going to do calculations based on these zero errors. Okay. And the next part here was random errors. These two were the divisions. Random errors. So here in the random error, you have, I said random error depends on two things. One is the object and the measurement. So basically, if we take the object, the errors caused by the object, there's no any calculation we can do. Like think how an object can cause an error. How? So think you have like you think you have metal ball. Okay, you have to take its radius and you have to do a real research about that metal ball. But what are your sibling, your sister or brother took it and put it down. Now it is smashed. Think a part of it is like born out. A part of it is born out. Now if you measure the diameter, it's going to give a false diameter. So that's an error. You can't do a research from it because the diameter is not the actual diameter. The diameter is going to be from here to this point. Understand? It's small stuff. You can understand that. Understand? So the object error, the errors caused by the object is a random error, and we can't. It's hard to calculate the errors caused by the object. So in A levels, we are not going to look into the errors caused by the object. So again here in random errors, we are going to calculate errors on the measurements. Okay. Errors on the measurements, by the measurements. So before coming to that, let's talk about something new. So you have a meter ruler. Take a meter ruler. You have a meter ruler, and you have small scales. These are millimeter scales. 1, 2, 4. This is 5, 6, 7, 8, 9, 10. Okay, like this. Like this. So you are going to measure something. You are going to measure something here. Something here. Okay. So it's hard to observe if this is really aligned with this point, because we can't zoom our images. We can't zoom it. We can't see it by using a magnifying glass also. We can't see if this is accurate. It is aligned accurately to this point. Okay. So there can be some errors after we take a measurement. Let's assume that this reading, this is going to be 85. 85. This 85 in the meter ruler. This is going to be 85 millimeters. 85 millimeters. 85 millimeters. Okay. That means 8.5 centimeters. 85 millimeters. So this reading is here. So the maximum possible error that is caused by this meter ruler is, someone can read it as 85, or what is the reading that, what's the scale that is adjacent to this reading? To this part, what's the adjacent scales? Divisions. This one and this one. This and this. So the maximum that you can differentiate is, sometimes it can be 85, or sometimes it can be the maximum, the worst case scenario. It can be 86. It can be the maximum between that. But you know that this is not more than 86. Then if this is 85, this is 86, and this is 87, right? You can clearly see that this is almost aligned to 85, almost aligned to 85, but you are sure, you are damn sure this is between, this is not more than 86, and this is not less than this is 4, 84, this is 84. This is not less than 84. You are very sure about that. Understand? So the worst case scenario is, if you take a measurement as 85, it can be 1 millimeter. This 1 millimeter is the least length that you can take from a meter ruler. For meter ruler, the least length is 1 millimeter. So the least length is known as the least count. So the least count should be added to the reading. So the worst case is, it can be 85, or plus 1, or minus 1. So I write that minus here. So every time when you are going to measure a reading from whatever the instrument, you should write the reading that you read as well as the least count here by writing a plus or minus symbol, the worst case scenarios. Understand? This is how you measure, how you do a measurement accurately. So it can be 85, or 1, or plus 1, or plus 7. So the maximum error is 86, the minimum is 84, and this is between this. Okay, this is the highest possible error. Highest possible error is the lowest possible error. Lowest reading. This is the lowest reading. Lowest possible error. This is the reading. Understand? Okay. So this least count and this 85. I'm going to use another example to compare this. What am I going to do? I'm going to take again that ruler, same ruler. I'm going to use the same ruler. Okay, I'm going to use the same ruler here. I'm going to use the same ruler here. Same ruler here. So these are the scales. 1, 2, 3, 4, and 5. Okay, this is 5th one. So now I'm going to measure. Shout, pay attention. Now I'm going to measure something really small. Something really small from the exact meter ruler. Okay, now I'm going to measure a really small length, and think this is 2 millimeters. This is 2 millimeters. Let's assume that is 2 millimeters. Okay. So what's the correct? How can I write this reading in that correct form? 2. This the least count of this is 1 millimeter. So I can write this. This can be 3 or this can be 1. It can be 3 or this can be 1. So I can write it as plus or minus 1. Plus or minus 1. Understand? So the highest possible error is the highest possible error. The highest possible error is 3. This is the reading and then this is 1. This is the highest possible error. Highest possible error. Possible error. And this is the lowest possible error. Lowest possible error. And this is the reading. This is the reading. Reading. Okay? Understand? So now, can anyone tell which one is a bit accurate? This or this? So now, this one is the error of this, what? Of this measurement. So the error part. This is the error part. This is an error. This one is the error. This is the error, and this is the what? The reading. Likewise, this is the error, and this is the reading. So this is the reading. Understand? This is the reading. So can you see that if we compare these two, the error is the ratio between the error and the reading here and the ratio between the error and the reading here is much greater. Understand? This is the error is half the size of the reading. Half the size of. So the error is 50% of the reading. A big error here. But here it's 1 out of 85. Understand? This is 1 out of the error is, if the reading is 85, this is 1 out of 85. Compared to this, this is, let's use another color. Blue. This is 1 out of 85. This is 1 out of 2. So which is greater? Greater. So this error is really large. So here the error that we keep behind the reading is known as the absolute error. Why? The absolute error in the sense that's the maximum error that can occur when you're taking a reading. So every time this absolute error is equal to the what count? Least count. So this error is also the absolute error of this reading. Absolute error of this reading, and this can be equal to the least count as well. Okay, but there are this is included in the A level syllabus. So in A level syllabus, they take the absolute error as the least count, but in other syllabuses like in Cambridge and other syllabus, they don't take least count as the absolute error. They take half of the least count as the absolute error. But in A level syllabus, keep this in mind. You take the absolute error as the least count. Okay, so if you take the fraction, between the error and the reading, 1 over 85, this error is known as the fractional error. What error? Fractional error. The fractional error ratio between the error and the reading. Okay, so the first one we learned here was absolute error. So it was absolute error. Absolute error. What's the absolute error? Here in this case, it's 1. It's 1. So this is the fractional error. So I said that this is half of the reading. 1 is half of 2. So this error is half of this reading. So if we take it percentage wise, it's going to be 50% of the reading. So we can propose this error in the percentage form also. So we can multiply this by 100 and write this in the percentage form. Now this is known as the percentage error. What error? Percentage error. And this is equal to how much? 85%. Not 85%. All it's going to be 100 divided by 85. That's not 85%. So we have to calculate this. For now, here if we calculate the percentage error of this part, it's going to be absolute error is going to be, I'm going to write this aligned to the absolute error is 1. Fractional error is 1 divided by 2. The percentage error is 1 divided by 2 100, it's going to be how many percentage? 50%. Understand? Okay. So this is the absolute error. It is every time equal to the least count in error syllables. So this is the fractional error, the ratio between the least count and the reading. This is going to be the percentage error. So if you take reading, two readings, you measure the length of a cube. Okay. Just think, you measure a length of a cuboid. You measure a length, width and the height of the cuboid. So you measure this length. Does the least count of the meter ruler changes? No, it's daily 1 millimeters. You measure the width of this cuboid. Does the least count of the meter ruler change? No. If you measure the height from that instrument again, does the least count change? No. So every time the reading is the part that's going to change. So in the fractional error, the least count is not going to change every time the percentage is going to change. You have to keep this in mind. Okay. So the denominator is going to change. So when the reading is greater, the fraction is going to be really low. When the reading is going to be much lower, it's going to be, the fractional error is going to be high. So compared to this 85, if you are taking 2 millimeters reading from a meter ruler, it is inaccurate. It's not accurate. So generally in physics, we think that 1% or less than 1%, if the error percentage is 1 or less than 1, then we take it as an accurate measurement. But if the error percentage is greater than 1, it is not going to be an accurate measurement. This is but this was implemented from 2000. I can't remember the year. This is a globally valid percentage. Okay, 1%. So 1 in the sense, if you take the percentage error, that is the that measurement is going to be the accurate, and the measurements that's lower than 1%. So it's better to explain like this. So this is the least count, and this is the reading, and let's take this as 100. So this is going to be equals to the percentage error. Okay. So the least count is not going to change. The reading is going to change. Let's take, this is going to increase. So when the reading is going to increase, the percentage is going to decrease. Why? Inversely proportional, right? So when the reading is increasing, the error is going to be decreased. So it is better to measure length of lengthy objects from a meter ruler than measuring length of small tiny objects. Understand? So to measure, to take accurate measurements of small tiny objects, that's why we use vernier calipers. Okay, that's why they created vernier calipers. So here, let's say that the percentage error is 1, the maximum error. If it is 1%, we are going to find what's the reading that we can take from a ruler, the maximum length. So the minimum length. Sorry, why? We can't take, it's inaccurate to take length, to measure the length of tiny objects, but it's accurate to take, we can take whatever the really longer object's length. It's accurate. It can be 1 meter, 2 meter. You can use the meter ruler again and again, and we can measure. It's not going to affect the accuracy, but the accuracy is going to get affected by the smaller distances. So there should be a minimum point, the minimum length that you can measure from a meter ruler. Okay, then that's the 1%. That's what they have introduced, 1%. If the percentage error is going to be equal to 1%, then that is considered as an accurate measurement. Less than it is much accurate, but more than this is but not accurate. So we are going to find this. So the least count of the the meter ruler is going to be 1 millimeters, and let's take the reading as n, and this is going to be multiplied by 100. So this to be 1, we have to put 100 here. So we can take this n here and put this 1 millimeter here, multiply by it by 100, and take this one to the denominator. Okay. So this is going to be how much? It's going to be 100 what? 100 millimeters. So the minimum shortest length that we can measure from a meter ruler is 100 millimeters. That means 10 centimeters. 10 centimeters. So it is not accurate to measure lengths lower than 10 centimeters, but you use a centimeter ruler. Understand? We use a centimeter ruler. It's like 15 centimeters. So we measure small stuffs also when we are doing construction, but that is also inaccurate. So if we use a meter ruler, if the least count is 1 millimeter, whatever the ruler, if the least count is 1 millimeter, we have to measure objects which is longer than 10 millimeters. Understand? 10 millimeters. Likewise, there are some questions in past papers, so we can do those stuffs also. So this is what I have to say now. Now we can complete the note. So come to the random error part. Random error. So when we are taking measurements, we have three types of errors. One is absolute error. The next one is fractional error. The next one is the percentage error. These are the calculation parts of errors. So this is going to be the absolute error, fractional error, and the percentage error. Okay. So let's fill the random error part. When a systematic error is removed from, there's a small note, when a systematic error is removed from a measurement, or when a systematic error is corrected, what remains will be the random error. I said that before. Okay. So we are going to write the note. Start right. A random error is an inconsistent. Start right. A random error is an inconsistent, non-reproducible deviation caused by a random error is an inconsistent, non-reproducible deviation caused by the object or the measurement process itself. Deviation caused by the object or the measurement process itself. Which can be reduced by repeated measurements. But does not require corrections or recalibration. Which can be reduced by repeated measurements, but does not require corrections or recalibration. Okay. So now it's 12 p.m. So let's wind up the session. So in the next class, we will talk about other things later. So I'm going according to a plan. Okay. So I have to finish the first unit. I have adequate time to finish the first unit. So if I don't get that time, what I'm going to do is I'm going to put night sessions. So you can join online or parallel. You can join it. You can watch the record. Okay. So likewise, these are the things that every tuition master does when it's near to the A level. They do this stuff. What if they can't cover the particular whole syllabus? What they do is they put extra classes as well as night seminars and cover up the syllabus. But I'm not going to do that in the final part. How I'm going to cover it from one unit to one unit. Understand? So I'm going according to a plan. So if there's a small, I think there will be some part remaining here in the first unit. So what I'm going to do is I'm going to put some night seminars or recordings. So now you'll have a free time. Now you are still starting, so you can watch the recordings or come to the online sessions. By joining those online sessions, in the initial part, you can increase your potential. Like in online sessions, you have to wait. You can't sleep. Sometimes I will do from 7 starting from 7 p.m, 8, 9, 10, 11. So until 11, you have to be focused. So likewise, you can increase your potential when if you're staying awake at the night. Understand? So most of the people, tuition sirs, what they do is they put midnight sessions from 12 to next day morning. Mostly they do those stuff. So we don't want to do those stuff at the final part. If we do that from the beginning, then you can increase your potential also. Understand? When you're doing at the last, you are going to be more stressed and you don't have adequate time. You have to do past papers, you have to do papers, you have other subjects now to complete the syllabus. So that's why if it's hard to complete, I'm doing this from unit to unit. I'm going to complete unit to unit. However, I'm going to cover the syllabus from unit to unit in a fixed amount of time. Understand? So get ready, boosted, and revise your note, theory note, and those stuffs. Okay. Right, and tell your friends to join Grant, and so you have you have to fill the application. Hard to fill down. Yeah. Well, you have the next class. So fill it and give it. If you are coming to the tomorrow's class, you can give it tomorrow. So tomorrow I'm not going to do a paper. I'm going to do the theory part. I mean, continue the practicals. So you can come and give the applications. If not, bring it in the next day. Bring it in the next week's class. Okay, fine. Goodbye.